In today's video, we're going to look at reversible reactions and see what we mean by the terms equilibrium and the position of equilibrium. Now, most chemical reactions look something like this, with the arrow in the middle pointing to the right to indicate that the reactants can turn into the products. This means that it's a one-way reaction. Once the carbon dioxide is formed, it won't break back down into carbon and oxygen. In other reactions though, like this one here, we have a double arrow, which tells us that the reaction is reversible. The top arrow tells us that ammonium chloride can break down into ammonia and hydrogen chloride, which we call the forward reaction, while the bottom arrow tells us that the ammonia and hydrogen chloride can also combine to reform the ammonium chloride, which we call the backward reaction. So because both of these can happen, we call it a reversible reaction. Now, the important thing to understand is that the forward and backward reactions can take place at different rates. At the beginning of the reaction, there'll be loads of ammonium chloride, but no ammonia or hydrogen chloride. So the forward reaction will be really fast, but the backward reaction won't have started yet. As the reactants turn into products though, the forward reaction will slow down, and the backward reaction will speed up. After a while, the rate will even out, and the forward and backward reactions will be going at exactly the same speed. At this point, the concentrations of the reactants and products won't change anymore, so we can say that the reaction is at equilibrium. So to clarify, at equilibrium, both reactions are still happening, but they effectively cancel each other out. So there's no overall change in the concentrations of the reactants or products. Of course, in reality, the molecules are still breaking down and reforming, but because they do so at the same rate, there's no overall change in the concentrations. Now, something to point out here is that just because the concentrations of the reactants and products are constant while at equilibrium, does not mean that they're the same as each other. For example, there could be lots of ammonium chloride and only a small amount of ammonia and hydrogen chloride. Or there could be lots of ammonia and hydrogen chloride, but only a small amount of ammonium chloride. In either case though, as long as the forward and backward rates are the same, then the reaction would still be at equilibrium. However, what would change when we have these different concentrations is the position of the equilibrium. When there are more products, like this, we would say that the equilibrium lies to the right. But if we had more reactants and fewer products again, then we'd say that the equilibrium lies to the left. This position of equilibrium can change depending on the conditions. For example, adding heat to this reaction encourages the forward reaction, meaning we'll have relatively more products, as the position of equilibrium moves to the right. On the other hand, if we cool the conditions of our reaction, it would push the position of equilibrium back to the left, so it would have more ammonium chloride again. Regardless of this position though, equilibrium can only be reached if the reversible reaction is done in a closed system, which means some kind of sealed environment from which none of the reactants or products can escape. Because if the products kept escaping, it would never reach equilibrium. The last thing we need to cover is that reversible reactions are always exothermic in one direction and endothermic in the other. For example, in this reaction, which shows the thermal decomposition of hydrated copper sulfate to anhydrous copper sulfate and water, the forward reaction is endothermic, and so the backward reaction is exothermic. If you're not familiar with these terms, hydrated just means that water is present, and anhydrous means that there's no water. Now, because the forward reaction is endothermic, it requires heat energy from the surroundings to work. So if we were to heat some hydrated copper sulfate, which exists as blue crystals, it will drive the reaction to the right, which evaporates off the water and leaves white anhydrous copper sulfate powder. If we then took away the heat and added some water to this powder though, it would drive the backward reaction, so the equilibrium would shift to the left, and reform our blue crystals of copper sulfate. And because this reaction is exothermic, it would re-release all of that energy it had just absorbed in the forward reaction. So to quickly recap everything, reversible reactions are those with a double arrow in the middle, which shows that they can react in both the forward and backward directions, one of which will have to be exothermic, and the other endothermic. And if these two rates are the same, then we say that the reaction is at equilibrium, and the concentrations of the reactants and products will remain constant. The position of equilibrium can change though, and will shift to the left or the right depending on the conditions.